This is a podcast about the history of the universe since the beginning of everything. Feel free to loop this video and go to sleep while listening to this podcast, and you will wake up as a wise man. My name is Donald John Trump, and now I will take you to a journey from the birth of the universe, from singularity to expansion. Chapter 1. The Singularity. In the beginning, there was nothing. No stars, no galaxies, no light, no time. The universe existed in an incredibly dense and hot state, compressed into a singularity, a point of infinite density and temperature. This singularity was the birthplace of everything we know today, a paradoxical realm where the laws of physics as we understand them break down. Chapter 2. The Big Bang. Approximately 13.8 billion years ago, something extraordinary happened. The singularity began to expand in an event known as the Big Bang. This was not an explosion in space, but rather an expansion of space itself, unfurling in all directions. The universe was born in a fraction of a second, in a process called cosmic inflation. Chapter 3. Cosmic inflation. During cosmic inflation, the universe expanded exponentially, growing from subatomic scales to macroscopic dimensions in less than a trillionth of a second. This rapid expansion smoothed out any irregularities and set the stage for the formation of the cosmos. Space itself was stretching, carrying everything within it. The temperature dropped as the universe expanded, but it was still an incredibly hot and energetic place. Chapter 4. Formation of fundamental particles. As the universe continued to expand and cool, the first fundamental particles began to emerge. Quarks and gluons, the building blocks of protons and neutrons, formed out of the energy of the early universe. These particles were in a hot, dense plasma, colliding and interacting in a high-energy soup. Chapter 5. Quark-gluon plasma. For the first microseconds of the universe's existence, it was dominated by a quark-gluon plasma, a state of matter where quarks and gluons moved freely. This plasma was so hot that quarks couldn't form protons and neutrons yet. But as the universe continued to cool, these quarks began to combine. Chapter 6. Formation of protons and neutrons. Around 1 microsecond after the Big Bang, the universe had cooled enough for quarks to combine and form protons and neutrons. These particles would later become the building blocks of atoms, but for now, they were simply part of the chaotic, high-energy early universe. Chapter 7. Nucleosynthesis. About 3 minutes after the Big Bang, the universe was cool enough for protons and neutrons to start combining into light nuclei in a process known as nucleosynthesis. This period lasted for about 17 minutes, during which the nuclei of hydrogen, helium, and small amounts of lithium were formed. These elements were the first building blocks of matter, setting the stage for the future formation of stars and galaxies. Chapter 8. Formation of atoms and the cosmic microwave background. As the universe continued to expand and cool, electrons began to combine with these light nuclei to form neutral atoms. This process, known as recombination, occurred about 380,000 years after the Big Bang. With the formation of neutral atoms, the universe became transparent, allowing light to travel freely. This light, the cosmic microwave background radiation, is the afterglow of the Big Bang and provides a snapshot of the infant universe. Chapter 9. The Dark Ages. Following recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies, just a vast expanse of dark, neutral hydrogen. The universe was cooling and expanding, setting the stage for the next epoch of cosmic history. Chapter 10: The First Stars and Galaxies. After millions of years of darkness, the first stars began to form from the gravitational collapse of dense regions of hydrogen gas. These stars were much larger and hotter than the stars we see today. Their formation marked the end of the Dark Ages and the beginning of the era of reionization, where the ultraviolet light from these first stars reionized the neutral hydrogen, allowing the universe to become transparent once more. These stars clustered into the first galaxies, illuminating the cosmos and creating the first complex structures. The gravity of these early galaxies pulled in more matter, forming larger galaxies and eventually the vast cosmic web of structures we observe today. The story of the universe is a story of constant change and evolution, from the chaotic birth of fundamental particles to the formation of stars and galaxies. Each stage sets the stage for the next, creating the rich and complex universe we see today. Now let's dive into the journey in detail. Chapter 1: The Singularity. In the beginning, there was an enigmatic point, a singularity. It was a realm beyond human comprehension, where the familiar concepts of space and time had no meaning. This singularity was the ultimate paradox, infinitely small, yet containing all the mass and energy that would one day form stars, planets, and life itself. The laws of physics as we know them ceased to exist here. Gravity and quantum mechanics collided in a cacophony of theoretical dissonance. The nature of the singularity. The singularity was not a location in space. Rather, it was a state of being where space itself was infinitely curved. In this bizarre realm, densities and temperatures reached inconceivable heights. Imagine 1,000,000,000,000 degrees packed into a point smaller than an atom. Here, time was so distorted that seconds stretched into eternities. Yet paradoxically, everything existed in an eternal instant. Physicists speculate that at this point, all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. This unification is a frontier of theoretical physics, explored through concepts like string theory and quantum gravity, yet remains beyond our experimental reach. Quantum fluctuations. Within this singularity, the concept of nothingness was imbued with the potential for everything. Quantum mechanics dictates that even in a perfect vacuum, pairs of particles and antiparticles can spontaneously appear and annihilate each other. These quantum fluctuations played a critical role in what was to come. The energy and perturbations within this singularity were far from uniform. Tiny, random fluctuations created regions of varying density and energy. The tension of instability. The singularity was not stable. The immense density and pressure created an environment ripe for change. Just as the core of a star can only hold off collapse for so long before exploding in a supernova, the singularity reached a tipping point. The exact mechanisms remain cloaked in mystery, but the balance between the unimaginable forces at play was delicate, like a tautly stretched rubber band on the verge of snapping. The moment of the Big Bang. Then, in an event that defies conventional understanding, the singularity underwent a rapid transformation. Time itself began at this moment. Space expanded outward in all directions, not into pre-existing space, but creating space as it went. This was the Big Bang, the moment of creation that marked the birth of the universe as we know it. It wasn't an explosion in space, but rather an explosion of space, the infinitely hot and dense beginning. In the immediate aftermath, the universe was a hot, dense plasma. Temperatures were so high that particles couldn't form stable atoms. Instead, they existed as a soup of quarks, gluons, electrons, and other fundamental particles. This primordial plasma was opaque, with light unable to travel freely. The universe was a seething, churning mass of energy and particles in constant, violent interaction. The inflationary epoch. In less than a trillionth of a second, a dramatic event called cosmic inflation occurred. During this brief period, the universe expanded exponentially, growing from a minuscule fraction of its current size to a scale vast enough to encompass the seeds of all future cosmic structures. This inflation smoothed out any irregularities, ensuring that the universe we observe today is remarkably homogeneous on large scales. Yet, the tiny quantum fluctuations imprinted during this epoch would later give rise to galaxies, stars, and planets. The end of singularity. By the end of inflation, the universe had cooled enough for the forces of nature to separate and distinct particles to form. The singularity was no longer a singularity. It had transformed into a rapidly expanding universe filled with potential. The high energy densities began to drop, and the universe entered a phase where it could evolve through the stages of nucleosynthesis, recombination, and the formation of the first atoms. Thus ended the reign of the singularity and began the era of the cosmos. From this infinitely small, dense point, the vast universe we inhabit today was born. The singularity's legacy is imprinted in every particle and every galaxy, a silent witness to the universe's tumultuous birth. Chapter 2: The Big Bang. Approximately 13.8 billion years ago, a momentous event unfolded, forever altering the course of existence. It was not an explosion as we understand it, but rather an incomprehensible expansion. The universe, in its infancy, burgeoned outward from a singular point. This singularity, a minuscule, infinitely dense realm, relinquished its grasp on the laws of physics as it swelled into an expanding cosmos. The unfolding of space. In an instant beyond measure, space itself began to unfurl. This expansion was not into pre-existing space, but an expansion of space itself. The fabric of the universe stretched relentlessly, carrying with it the seeds of galaxies, stars, and the elements that would compose all future matter. The temperature of creation. In those early moments, the universe brimmed with unimaginable heat and energy. The fabric of space was saturated with a searing plasma of fundamental particles, quarks, gluons, electrons, engaged in a frantic dance of creation. This primordial inferno was so intense that even the concept of atomic nuclei was inconceivable. Instead, the universe was a maelstrom of particles and energy, bound by the nascent forces that would come to govern its evolution. The onset of cosmic inflation. In the blink of an eye, cosmic inflation began. This epoch of rapid expansion stretched the universe beyond comprehension, smoothing out any irregularities that may have arisen from its explosive birth. Inflation acted as a cosmic iron, flattening the curvature of space and setting the stage for the universe's subsequent evolution. The fading echoes of creation. As the universe expanded, its temperature plummeted. From an unimaginable inferno, it cooled to a state where quarks could coalesce into protons and neutrons. This transition marked the dawn of a universe poised for the next chapter of its story, one that would see the emergence of the first atomic nuclei and the eventual formation of the first elements. The legacy of the Big Bang. The Big Bang was not merely the birth of the universe. It was the genesis of all that we know, the wellspring from which galaxies, stars, and planets would emerge. Its echoes reverberate through the cosmos in the form of the cosmic microwave background radiation, a faint whisper of the universe's fiery infancy. A universe in flux. From its humble beginnings in an inconceivable singularity, the universe embarked on a journey of transformation. It evolved from a dense, hot crucible of particles into the expansive cosmos we behold today. The Big Bang ignited a cosmic symphony of creation, where the forces of nature sculpted the intricate tapestry of galaxies and stars that adorn the heavens. The eternal mystery. Yet, amidst the clarity brought by scientific inquiry, the origin of the universe remains an enigma. The Big Bang serves as both a testament to human curiosity and a reminder of the vast unknowns that still lie beyond our reach. As we gaze upon the night sky, we are witness to the legacy of that singular moment, a universe born from the depths of a primordial fire, forever expanding into the unknown. Chapter 3: Cosmic Inflation. Following the intense energy release of the Big Bang, the universe underwent a rapid expansion phase known as cosmic inflation. This period, occurring shortly after the initial moments of creation, initiated an exponential growth of space itself. The scale of this expansion was extraordinary, transforming the universe from subatomic scales to macroscopic dimensions within a fraction of a second. During cosmic inflation, the fabric of space stretched exponentially, smoothing out any irregularities or variations in density that may have existed initially. This smoothing effect is crucial as it explains why the universe appears so uniform on a large scale today. Even minute quantum fluctuations, arising from the uncertainty principle in quantum mechanics, were magnified to become the seeds of structure formation in the universe. The energy driving cosmic inflation was immense, derived from the vacuum energy associated with a hypothetical scalar field called the inflaton. As the universe expanded, this field remained in a high-energy state, driving the accelerated expansion. The inflationary epoch came to an end when the inflaton field decayed, releasing its stored energy into the universe. This process, known as reheating, marked the transition to the subsequent phases of cosmic evolution. The evidence for cosmic inflation comes from several sources, including observations of the cosmic microwave background, CMB, radiation. Tiny temperature fluctuations in the CMB provide a snapshot of the universe when it was just 380,000 years old, offering strong support for the predictions of inflationary theory. These fluctuations correspond to slight variations in the density of the early universe, which seeded the formation of galaxies and large-scale structures observed today. Cosmic inflation not only explains the uniformity of the universe, but also provides a framework for understanding its large-scale structure and composition. It remains a cornerstone of modern cosmology, supported by both theoretical models and observational data, shaping our understanding of the universe's earliest moments and its subsequent evolution over billions of years. Chapter 4: Formation of Fundamental Particles. As the universe continued its rapid expansion after the Big Bang, it entered a phase where fundamental particles began to emerge from the primordial soup of energy. These particles would eventually form the basis of all matter and structures in the universe. In the intense heat and energy of the early universe, the first particles to form were quarks and gluons. Quarks are elementary particles that come in 6 types, or flavors: up, down, charm, strange, top, bottom, and they are bound together by gluons, the carriers of the strong nuclear force. During the initial microseconds after the Big Bang, the universe was too hot and dense for quarks to bind together into stable particles like protons and neutrons. Instead, the universe existed in a state known as a quark-gluon plasma. In this state, quarks and gluons moved freely, constantly interacting and colliding with each other. It was a chaotic soup where the distinction between different particles was blurred. The existence of this quark-gluon plasma was confirmed experimentally in particle accelerators such as the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory and the Large Hadron Collider, LHC, at CERN. These experiments recreate conditions similar to those just after the Big Bang, allowing scientists to study the behavior of quarks and gluons under extreme conditions. As the universe continued to expand and cool, reaching temperatures of about a few trillion degrees Celsius, a critical transition occurred. Approximately 1 microsecond after the Big Bang, the universe had cooled enough for quarks to begin binding together to form protons and neutrons. This process is known as hadronization or hadron formation. Protons and neutrons are baryons, a type of particle made up of 3 quarks bound together by gluons. Protons are composed of 2 up quarks and 1 down quark, UD, while neutrons consist of 1 up quark and 2 down quarks, UD. The formation of protons and neutrons marked a significant milestone in the evolution of the universe. These particles would later play a crucial role in the formation of atomic nuclei during the process of nucleosynthesis, which occurred a few minutes after the Big Bang. The study of fundamental particles and their interactions provides deep insights into the nature of the early universe and the fundamental forces that govern it. From the initial chaos of the quark-gluon plasma to the structured formation of protons and neutrons, the story of particle formation in the early universe is a testament to the intricate physics that shaped our cosmic history. Chapter 5: Quark-gluon Plasma. In the immediate aftermath of the Big Bang, the universe was a seething, hot soup of fundamental particles where quarks and gluons moved freely in a state known as quark-gluon plasma. This phase, which lasted for microseconds after the Big Bang, is crucial in understanding the early evolution of the universe. The quark-gluon plasma. Quarks are fundamental particles that come in 6 types, or flavors: up, down, charm, strange, top, and bottom. They are bound together by gluons, which are the carriers of the strong nuclear force. At extremely high energies and temperatures, such as those just after the Big Bang, the strong force is so powerful that quarks and gluons do not bind together to form stable particles like protons and neutrons. Instead, they exist in a deconfined state, where they move freely and interact strongly with each other. Conditions in the early universe. During the first microseconds of the universe's existence, the temperature was incredibly high, reaching trillions of degrees Celsius. This extreme heat was sufficient to break down the bonds between quarks and gluons, allowing them to exist independently in a plasma state. The density of this quark-gluon plasma was immense, with particles colliding and interacting with each other at a rapid pace. Experimental confirmation. The existence of quark-gluon plasma was first predicted by theoretical physicists studying the early universe. Experimental evidence supporting its existence came from high-energy particle colliders such as the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory and the Large Hadron Collider, LHC, at CERN. These colliders accelerate heavy ions, such as gold or lead nuclei, to nearly the speed of light and smash them together, recreating conditions similar to those just microseconds after the Big Bang. Studying quark-gluon plasma. By studying the properties of quark-gluon plasma, scientists aim to understand the fundamental nature of the strong nuclear force and how it operated in the early universe. The plasma's behavior under extreme conditions provides insights into the phase transitions that occurred as the universe expanded and cooled. Transition to hadrons. As the universe continued to expand and cool, reaching temperatures of about a microsecond after the Big Bang, the quark-gluon plasma began to undergo a phase transition known as hadronization or hadron formation. This transition marked the point where quarks started to bind together to form composite particles called hadrons, such as protons and neutrons. Legacy of quark-gluon plasma. The study of quark-gluon plasma remains a vibrant area of research in particle physics and cosmology. It offers a glimpse into the extreme conditions that prevailed in the early universe and helps us understand how the fundamental particles and forces of nature evolved over time. The legacy of quark-gluon plasma continues to shape our understanding of the cosmos and the fundamental physics governing it. Chapter 6: Formation of protons and neutrons. Approximately 1 microsecond after the Big Bang, as the universe continued to expand and cool, the conditions were ripe for quarks to begin binding together to form stable particles known as protons and neutrons. This phase, known as hadronization or hadron formation, marked a significant transition in the early universe's evolution. Hadronization process. Hadronization refers to the process where quarks and gluons, which existed in a deconfined state in the quark-gluon plasma, began to bind together to form composite particles called hadrons. Hadrons are particles that experience the strong nuclear force and are composed of quarks bound together by gluons. Protons and neutrons. The most familiar hadrons are protons and neutrons, which are baryons. Protons are composed of 2 up quarks and 1 down quark, UD, while neutrons consist of 1 up quark and 2 down quarks, UD. These combinations of quarks and gluons stabilize into particles that would later become the building blocks of atomic nuclei. Energy conditions. During hadronization, the universe had cooled to temperatures where the strong nuclear force could bind quarks together into stable configurations. The energy densities were still incredibly high, but not as extreme as during the quark-gluon plasma phase. As quarks combined to form protons and neutrons, the universe began its transition towards a more structured and less chaotic state. Formation of light nuclei. Following the formation of protons and neutrons, the universe entered a phase known as nucleosynthesis. Approximately 3 minutes after the Big Bang, the temperature and density conditions were right for protons and neutrons to start combining into light nuclei like hydrogen, 1 proton, helium, 4, 2 protons and 2 neutrons, and small amounts of lithium, 7. Role in cosmic evolution. The formation of protons and neutrons laid the foundation for the future evolution of the universe. These particles, along with electrons and photons, light particles, would go on to form the first atoms during the epoch of recombination, which occurred about 380,000 years after the Big Bang. The ability of protons and neutrons to bind together into stable nuclei was crucial for the eventual formation of stars and galaxies. Experimental insights. The processes of hadronization and nucleosynthesis have been studied and confirmed through both theoretical models and experimental observations. Particle accelerators, such as the Large Hadron Collider, LHC, at CERN, have provided valuable insights into the behavior of quarks and gluons under extreme conditions, supporting our understanding of the early universe's formation. Legacy of protons and neutrons. Protons and neutrons continue to play fundamental roles in the structure and evolution of the cosmos. Their stability and ability to form atomic nuclei allowed for the creation of elements heavier than hydrogen and helium through stellar nucleosynthesis. Thus, the formation of protons and neutrons represents a pivotal moment in cosmic history, setting the stage for the emergence of complex structures and, eventually, life itself. Chapter 7. Nucleosynthesis. Approximately 3 minutes after the Big Bang, the universe had expanded and cooled sufficiently for protons and neutrons to begin combining into light nuclei in a process known as nucleosynthesis. This period was crucial in determining the elemental composition of the universe and laid the foundation for the formation of stars and galaxies. Conditions for nucleosynthesis. During the first few minutes after the Big Bang, the temperature of the universe had dropped to around 1 billion degrees Celsius. At this point, the density of protons and neutrons was high enough that they could start to form stable atomic nuclei through nuclear reactions. The primary nuclei synthesized during this period were hydrogen, 1, protium, helium, 4, and small amounts of lithium, 7. Formation of nuclei. The formation of nuclei proceeded through a series of nuclear reactions, primarily involving the fusion of protons and neutrons. The most significant reactions during nucleosynthesis were proton-proton chain, hydrogen nuclei, protons, fused together to form helium nuclei, alpha particles. Deuterium formation, 2 protons and 1 neutron combined to form deuterium, hydrogen, 2. Helium synthesis, deuterium nuclei fused with protons and neutrons to produce helium, 4. These reactions were governed by the strong nuclear force, which binds protons and neutrons together in atomic nuclei. The balance between the expansion rate of the universe and the rate of nuclear reactions determined the final abundance of each element produced during nucleosynthesis. Abundance of elements. By the end of nucleosynthesis, the universe was composed primarily of hydrogen, about 75% by mass, and helium, about 25% by mass. Only trace amounts of heavier elements, such as lithium, were synthesized during this early phase. The exact ratios of these elements provide critical insights into the conditions prevailing in the universe shortly after the Big Bang. Experimental confirmation. The predictions of nucleosynthesis theory have been tested and confirmed through observational evidence, such as the cosmic microwave background radiation, CMB, and the abundance of light elements in the universe. The CMB, which is a remnant radiation from the early universe, exhibits small temperature fluctuations that reflect the density variations of the universe during nucleosynthesis. Legacy of nucleosynthesis. Nucleosynthesis marks a crucial phase in cosmic evolution, as it set the initial conditions for the formation of stars and galaxies. The helium produced during nucleosynthesis played a pivotal role in the formation of the first stars, which would later become the sites for heavier element synthesis through stellar nucleosynthesis processes. Overall, nucleosynthesis provides a fundamental framework for understanding the elemental composition of the universe and the processes that governed its early evolution. It represents a testament to the power of nuclear physics in shaping the cosmos from its earliest moments. Chapter 8. Formation of atoms and the cosmic microwave background. Approximately 380,000 years after the Big Bang, the universe had expanded and cooled to the point where protons and electrons could combine to form neutral atoms in a process known as recombination. This epoch marked a pivotal transition in the history of the universe, leading to the formation of the first atoms and the release of the cosmic microwave background, CMB, radiation. Recombination process. During the first few 100,000 years after the Big Bang, the universe was filled with a hot, dense plasma consisting of protons, electrons, and photons, particles of light. The temperature of the universe at this time had cooled to around 3,000 degrees Celsius, which was cool enough for electrons to be captured by protons to form neutral hydrogen atoms. Formation of neutral atoms. As the universe continued to expand, the density of the plasma decreased. Electrons and protons combined through the process of recombination, where electrons settled into low-energy orbits around protons, forming neutral hydrogen atoms, one proton and one electron. This transition from a plasma of ions, charged particles, to a neutral gas allowed photons to travel freely through space, marking the universe's transition from opaque to transparent. Cosmic microwave background, CMB, radiation. The formation of neutral atoms had a profound effect on the universe's appearance. Before recombination, photons were constantly scattered by free electrons in the plasma, preventing them from traveling far. However, once recombination occurred, photons were able to travel freely through space without being scattered. These photons, which were emitted during recombination, formed the cosmic microwave background radiation. Properties of the CMB. The CMB is a faint glow of radiation that permeates the entire universe. It is often referred to as the afterglow of the Big Bang because it represents the thermal radiation left over from the hot, early universe when it became transparent. The CMB is nearly uniform in all directions and has a temperature of about 2.7 Kelvin, minus 270.45 degrees Celsius or minus 454.81 degrees Fahrenheit, making it one of the most precisely measured phenomena in cosmology. Discovery and confirmation. The existence of the CMB was predicted by theorists like George Gamow, Ralph Ulfer, and Robert Herman in the 1940s and was discovered accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories. Their discovery provided strong evidence for the Big Bang Theory and transformed our understanding of the universe's early history. Legacy of the CMB. Studying the CMB has provided valuable insights into the universe's composition, age, and overall structure. Tiny fluctuations in the CMB temperature across the sky, known as anisotropies, reveal information about the universe's initial conditions and the formation of cosmic structures like galaxies and galaxy clusters. Modern observatories, such as the Planck satellite and ground-based telescopes, continue to study the CMB with unprecedented precision, further refining our understanding of cosmology and the early universe. The era of recombination and the formation of the CMB radiation represent critical milestones in cosmic history, marking the transition from the universe's hot, dense infancy to its subsequent evolution into the vast and complex cosmos we observe today. Chapter 9. The Dark Ages. After the universe became transparent due to recombination, a period known as the Dark Ages ensued, lasting for hundreds of millions of years. This epoch represents a crucial but mysterious chapter in cosmic evolution, characterized by the absence of stars, galaxies, and any significant sources of light. The end of recombination. Approximately 380,000 years after the Big Bang, neutral atoms filled the universe, allowing photons to travel freely. The cosmic microwave background, CMB radiation, emitted during recombination, continued to permeate space, gradually cooling as the universe expanded. Darkness descends. With the transition to neutral hydrogen and the decrease in free electrons, the universe entered a state of darkness. The absence of stars and galaxies meant that there were no significant sources of visible light or other electromagnetic radiation. The universe was a vast expanse of cold, dark space, populated only by diffuse clouds of hydrogen gas. Formation of structure. Despite the darkness, gravitational forces were at work, causing slight density fluctuations in the primordial hydrogen gas. These fluctuations were remnants of the quantum fluctuations present in the early universe and were amplified over time by the force of gravity. Over millions of years, these fluctuations grew, leading to the formation of denser regions where gas could eventually collapse to form the first stars and galaxies. Cosmic evolution. The Dark Ages marked a critical period in cosmic evolution, as the universe transitioned from its simple beginnings of hydrogen and helium into a more complex structure. The seeds of future galaxies were sown during this time, as gravitational instabilities continued to shape the distribution of matter in the universe. Observational challenges. Understanding the Dark Ages is challenging because there are few direct observational clues from this era. The lack of visible light or other electromagnetic signals makes it difficult to observe the universe directly during this period. Instead, scientists rely on indirect methods, such as studying the cosmic microwave background, simulations, and theoretical models to reconstruct the conditions and processes that occurred. Theoretical insights. Theoretical models suggest that the Dark Ages were a time of gradual transition and evolution. Hydrogen gas continued to cool and contract under the influence of gravity, forming increasingly dense clouds and filaments. These structures eventually became the birthplaces of the first generation of stars, marking the end of the Dark Ages and the beginning of the cosmic dawn. Legacy of the Dark Ages. The Dark Ages represent a pivotal phase in the universe's history, setting the stage for the formation of stars, galaxies, and ultimately, the complex structures observed in the universe today. Studying this epoch provides insights into the conditions that governed the early universe and the processes that led to the emergence of cosmic structure. Future exploration. Current and future observatories, such as the James Webb Space Telescope, JWST, and ground-based facilities, aim to peer deeper into the universe's past. By observing the faint signals from the Dark Ages and cosmic dawn, astronomers hope to uncover more about the first stars and galaxies and the evolution of the universe from its mysterious beginnings to the present day. The Dark Ages remain a tantalizing frontier in cosmology, holding the secrets to the universe's infancy and the origins of cosmic complexity. Chapter 10. Birth of the First Stars and Galaxies. After millions of years of cosmic darkness, the universe underwent a profound transformation with the birth of the first stars and galaxies. This epoch, known as the Cosmic Dawn, marked a pivotal moment in the history of the cosmos, shaping its evolution into the richly structured universe we observe today. Formation of the first stars. Around 100 to 200 million years after the Big Bang, dense pockets of hydrogen gas began to collapse under the force of gravity, forming the first stars. These stars were composed primarily of hydrogen and helium, the two lightest elements synthesized during nucleosynthesis. The collapse of gas clouds into stars marked the end of the Dark Ages and initiated a new era of stellar evolution. Protostellar evolution. As the gas clouds collapsed, they heated up due to gravitational compression. At the cores of these collapsing clouds, temperatures and pressures rose to the point where nuclear fusion reactions ignited. These reactions fused hydrogen nuclei into helium, releasing vast amounts of energy in the form of light and heat. The first stars, often referred to as population-free stars, were much larger and hotter than stars like the Sun, with some estimates suggesting they could have been hundreds of times more massive. Impact on the universe. The emergence of the first stars had profound consequences for the universe. Their intense radiation and stellar winds altered the surrounding environment, ionizing the hydrogen gas once more in a process known as reionization. This epoch, which occurred roughly between 150 million to 1 billion years after the Big Bang, marked the transition from a universe filled with neutral hydrogen to one dominated by ionized plasma. Formation of galaxies. The formation of stars also facilitated the formation of galaxies. Gravity caused clusters of stars to come together, along with gas and dust, forming the first galaxies. These galaxies initially consisted of irregular shapes and were smaller and less structured than the spiral and elliptical galaxies observed today. Over time, galaxies merged and evolved through processes like star formation, supernovae explosions, and interactions with neighboring galaxies. Observational evidence. Studying the birth of the first stars and galaxies is challenging due to their faintness and the vast distances involved. However, advancements in observational astronomy, including telescopes like the Hubble Space Telescope and upcoming facilities like the James Webb Space Telescope, JWST, have allowed astronomers to peer back in time and observe distant galaxies that existed billions of years ago. Theoretical insights. Theoretical models, supported by observations, suggest that the universe evolved from a simple, homogeneous state shortly after the Big Bang to a complex and diverse cosmos with galaxies of various shapes, sizes, and compositions. Understanding the processes that led to the formation of the first stars and galaxies provides crucial insights into the fundamental forces and physical laws governing the universe's evolution. Legacy of Cosmic Dawn. The Cosmic Dawn represents a critical juncture in cosmic history, marking the transition from a universe dominated by darkness and simple atomic elements to one filled with luminous stars, galaxies, and cosmic structures. It laid the foundation for the subsequent evolution of a universe, including the formation of heavy elements through stellar nucleosynthesis, the development of galaxy clusters, and the emergence of planetary systems capable of supporting life. Future exploration. Future astronomical missions and observatories, such as the JWST, are poised to unlock even more secrets of the cosmic dawn. By studying the earliest galaxies and the conditions surrounding their formation, scientists hope to gain deeper insights into the origins of cosmic structure, the nature of dark matter and dark energy, and the potential for life elsewhere in the universe. The birth of the first stars and galaxies stands as a testament to the universe's capacity for transformation and complexity, setting the stage for billions of years of cosmic evolution and exploration. The story of the universe is one of continual transformation and exploration, spanning over 13.8 billion years from its explosive beginning in the Big Bang to the vast and intricate cosmos we marvel at today. From the primordial soup of quarks and gluons in the intense heat of the early universe to the formation of protons, neutrons, and eventually the first atomic nuclei, each epoch has left its mark on the fabric of existence. Through the Dark Ages, where the universe was shrouded in darkness and gravitational forces silently sculpted the distribution of matter, to the cosmic dawn that heralded the birth of the first stars and galaxies, the cosmos has evolved through cycles of creation, destruction, and rebirth. Stars, born from the gravitational collapse of gas clouds, became the crucibles where elements heavier than helium were forged in fiery cores and scattered into the cosmos through supernova explosions. Galaxies, spanning vast distances and ranging from spirals to ellipticals, emerged as cosmic cities of billions of stars, bound together by the invisible threads of dark matter. They evolved through mergers and collisions, creating intricate cosmic webs that weave through the universe, shaping its structure on the largest scales. Amidst this cosmic tapestry, planets formed around stars, some resembling our own Earth, where conditions were just right for life to emerge and evolve. The quest to understand our place in the universe has driven humanity to explore the depths of space, from the moon and planets of our own solar system to the distant reaches of the cosmos. Observatories like the Hubble Space Telescope have peered billions of light-years into space, capturing images of galaxies in their infancy and revealing the echoes of the Big Bang in the cosmic microwave background radiation. Ground-based telescopes and future missions, such as the James Webb Space Telescope, promise to unveil even more mysteries, from the nature of dark energy and dark matter to the potential for life beyond our solar system. As we stand on the brink of a new era of discovery, the story of the universe continues to unfold before us, inviting us to ponder our origins, our place in the cosmos, and the fundamental laws that govern existence itself. It is a story of wonder, curiosity, and exploration, a testament to the human spirit's enduring quest for knowledge and understanding. In the vastness of space and time, the universe beckons us to explore its mysteries, to uncover the secrets of its birth and evolution, and to contemplate the possibility of other civilizations amidst the billions of stars and galaxies that adorn the cosmic stage. As we embark on this journey of discovery, we are reminded of our interconnectedness with the cosmos and the profound beauty of the universe that surrounds us. Thus, the ending of the universe's story is not a conclusion but a beginning of new questions, new discoveries, and new horizons yet to be explored. It is a reminder that our journey through the cosmos is just beginning, and the universe, with its boundless mysteries and infinite possibilities, awaits our continued exploration and understanding. Reflecting on the vastness of the cosmos and the journey of discovery, we are reminded of our boundless potential to explore, learn, and create. As I, Donald Trump, play Minecraft, I am struck by the parallels between crafting virtual worlds and the monumental challenges we face in reality. In both realms, innovation and determination drive progress, and every decision shapes the landscape of our achievements. As Carl Sagan eloquently said, somewhere, something incredible is waiting to be known. Each of us, like stars in the night sky, carries within us the spark of curiosity and the capacity to reach beyond our limits. In the words of Maya Angelou, we delight in the beauty of the butterfly, but rarely admit the changes it has gone through to achieve that beauty. Similarly, our quest for knowledge and understanding, whether through exploring the universe or building worlds in Minecraft, is a testament to our resilience and ingenuity. So, as I, Donald Trump, navigate the complexities of existence, let us embrace our curiosity, celebrate our achievements, and continue to reach for the stars. For in the grand tapestry of the cosmos, each of us has a part to play, a part that is unique, valuable, and filled with infinite possibilities. And remember, as I once pondered, in life, you have to rely on the past, and that's called history. In Minecraft, as in life, every block placed and every creation built is a testament to our creativity and vision. It is in these virtual worlds that we harness the power to shape our environments, forge alliances, and craft our destinies. So, let us continue to explore, create, and innovate, together, forging a future where our collective dreams become reality. For it is through our shared efforts and individual contributions that we leave a lasting legacy for generations to come. The way I am talking right now is different because I don't have to act as someone who stands in front of the crowd, and that is everything I have for you. Please share, like, and subscribe to spread this story for everyone. If you awake, please comment below if you have any question. And again, thanks you for watching from the bottom of my heart.